Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Professor Alex Schuppe. Alex earned his bachelor's at the University of Texas at Austin, where he carried out undergraduate research in the Siegel group. He subsequently completed his doctoral work in the Newhouse group at Yale, where he did some very exciting work in total synthesis that he'll discuss today. He became an Arnold O. Beckman postdoctoral research fellow in the Buchwald Lab at MIT before starting his independent career at Vanderbilt. And with that, I'll let you get started, Alex. Thank you very much for coming on today.
Thank you so much, Matt, for that really kind introduction. I'm really excited to be part of this platform and to tell everyone today about some work from my PhD in the Newhouse group at Yale University. And today I'll tell you two stories on the total synthesis of various Limonoid alkaloids. The Limonoids are an extremely diverse class of natural products, comprised of over 1,000 known congeners that are broadly brought together by this basic limonoid skeleton, containing a highly conserved 4,4,8-trimethyl-17-furanyl steroidal skeleton. But as you'll notice even on this slide with these four examples, this skeleton can undergo a wide variety of ring rearrangements and oxidative state manipulations to access really a plethora of structural complexity. But aside from these topologically unique molecules, we were really intrigued by this class of natural products due to their potent biological activity, including neuroprotective and anti-cancer activity. Limonin, the parent family member in this class of natural products, was first isolated in 1841 from citrus fruits, but its structure wasn't fully characterized until 1960 by degradation in X-ray crystallography studies. But most of the biologically interesting and structurally complex molecules on this slide, including these Limonoid alkaloids, are isolated in minute quantities from the Melicae flowering plant. And another thing that really caught our attention was the highly conserved B, C, and D rings highlighted in red in this structure. And we wondered if we could design a strategy to access this conserved core. We wanted to gain insight by the landmark studies in this field, including the work from Corey and Yamashita that took linear polyolefin precursors and rapidly cyclized them to access the carbocyclic core of the molecule. But at this point, various functional group manipulations, including oxidation state manipulations, had to be carried out to access a single natural product. And really at the outset, what we wanted to design was a convergent fragment coupling approach that would allow us to mix and match different fragments at various stages in the synthesis to access a wide array of different structurally complex and different Limonoid natural products. And we first demonstrated this strategy in the synthesis of Andirolide N, which contains this stereochemically dense bicyclononane with an appended hemiketal bridging ring. In looking into the literature, we found this really intriguing related natural product, 8-alpha-hydroxycarapin, and were able to recapitulate its biosynthetic reorganization hypothesis through simple treatment of sulfuric acid. And retrosynthetically, once again, we could trace 8-alpha-hydroxycarapin back to this degraded limonoid isoodiratin through bisecting this bicyclononane through an acylation and Michael type approach. Now today I really want to focus in on these really intriguing Limonoid alkaloids, which are typified by granitumine A and xylogranatopyridine B. And one thing that's really intriguing about these natural products is they're actually purported to arise from a molecule such as 8-alpha-hydroxycarapin. An oxidation event at the C9 position now primes this C9-C10 cleavage through a retroaldol type process, and subsequent beta-alkoxy elimination now arrives at this key diketone intermediate, in which this diketone can diverge in the presence of an ammonium equivalent to access these two different classes of Limonoid alkaloids. And although we thought we may be able to recapitulate this biosynthetic proposal, we thought a more direct and convergent strategy would be to bisect this highly conserved pyridine structure in the middle of these molecules through a de novo type strategy. And therefore we first employed this strategy to bisect this central pyridine ring in the synthesis of xylogranatopyridine B. Retrosynthetically, we considered first simplifying this A ring of the molecule, which would bring us back to the tetracyclic core of xylogranatopyridine B. In the forward sense, we thought we could decorate this A ring through a late-stage incorporation of this benzylic ketone and vicinal difunctionalization reaction. Now at this point, we considered de novo type pyridine strategies that would allow us to cleave retrosynthetically this CN bond and CC bond, and gained a lot of insight from this work by Libeskind and coworkers, which took these perfluorinated oxime benzoates and vinyl boronic acids to initially gain access to a Chan-Lamb coupling adduct, which was now poised to undergo a 6-pi electrocyclization to furnish the pyridine. In our case, we wanted to employ the more stable oxime benzoate as well as the corresponding vinyl staining, which would be more amenable to multi-step synthetic sequences. Once again, retrosynthetically, we thought we could cleave these two carbon-carbon bonds highlighted in orange, which would bring us back to this beta-stanol enone. And in the forward sense, we could access this coupling fragment through successive aldol-type cyclization reactions. Now, in considering how we would make this beta-stanol enone, we initially considered the conventional Stork-Danheiser type approach, which would involve activation of a 1,3-di ketone, methylation, and then subsequent addition of a stanol organometallic species. However, one thing that was really clear to us is when 1,3-di ketone starting materials are not commercially available, they can be quite challenging to access, and we'll actually see an example of this later on in the talk. And therefore, we wondered, could we employ widely available enone precursors and engage this enone selectively in a 1,4 conjugate addition reaction with a stanol nucleophile, which would then provide this bimetallic intermediate, in which if we could undergo a selective transmetallation of the metal enolate substructure in the presence of an allyl stannane with an allyl palladium catalyst, we may be able to gain access to our requisite product after beta hydride elimination. And this would really gain insight from previous work done in the Newhouse lab on alpha-beta dehydrogenation reactions utilizing allyl palladium catalysis, specifically the dehydrogenation of ketones to enones. However, the goal of this transformation would be to begin with an enone precursor and engage this enone selectively in a 1,4 conjugate addition reaction with a stanol nucleophile, in which we thought the identity of the formed metal enolate structure would really dictate the outcome of the selective transmetallation with an allyl palladium catalyst. After transmetallation, a palladium enolate would be formed that upon beta hydride elimination would furnish the product concomitantly with a palladium hydride. Upon reductive elimination, propene would be formed along with palladium 0, which could undergo oxidative addition with an allyl electrophile to reform the active allyl palladium catalyst. In terms of optimization of this palladium catalyzed beta stanylation, we were really focused on the identity of this metal enolate, which would be generated from the addition of a stanol nucleophile. And therefore, we thought that this identity would really affect the yield and conversion to our desired product. And we did indeed find this to be the case when we utilized tributyl stanolithium. We got both the highest yields and conversions to our desired product, but modulation of the identity of this nucleophilic species either to the organozinc or organocopper species resulted either in a lower yield or no yield respectively. And with these optimized conditions in hand, we could now affect the decagram scale synthesis of this beta stanol enone, which was necessary for the total synthesis of xylogranatopyridine B, but we could also extend this to the beta stanylation of complex molecules, as well as the beta silation of enones and enoates. By modulation of the identity of the nucleophilic species to triorganozincates, we could also affect the beta alkylation of various enone precursors. With a really robust approach to our beta stanol enone starting material, we sought to affect the total synthesis of xylogranatopyridine B through this modified Libeskind pyridine synthesis with these two key starting materials, in which I'll begin by telling you how we approach the synthesis of this oxime benzoate starting material. And this would eventually become the A ring in the molecule, this fragment that's highlighted in blue in the natural product structure. Beginning with this commercially available enone starting material, we could engage this with a methyl cuprate nucleophile, entrapping with TMS chloride provided the intermediate enoxysilane. And to this, we could undergo this really neat reaction that was developed by Yamamoto and coworkers involving the in situ formation of TIPS nitrite, in which this enoxysilane could engage TIPS nitrite and after hydrolysis form the alpha ketoxime. Now, to this ketone structure, we could undergo a methionylation reaction and subsequent benzoylation revealed the A-ring coupling fragment in 4 steps, and this was a really robust sequence. We now considered how we would make the C and D ring coupling fragment, which would eventually become these 2 rings highlighted in blue in the natural product. And this began with the aforementioned beta-stanol enone. And to this structure, we could effect a diastereoselective aldol reaction and subsequent acylation with acetic anhydride provided the corresponding benzylic acetate. Upon deprotonation with lithium TMP, an intramolecular cyclization reaction was triggered, revealing the corresponding lithium alkoxide that could engage Burgess reagent in a dehydration reaction to provide the vinyl stannane coupling fragment in a 5-step sequence. With a really robust protocol to both of our 2 key fragments, we were ready to tackle the modified Libeskind pyridine synthesis, in which we found copper acetate and quinupridine were ideal conditions for achieving the Chan-Lamb coupling. This intermediate was poised to undergo a rapid and selective 6-pi electrocyclization. Subsequent aerobic oxidation provided the tetracyclic core of the molecule. Comparing this to the natural product, we now needed to undergo a selective oxidation at the C1 position in the presence of the C11 and more electron-rich furan. After examining a variety of reagents and conditions, we eventually found that this chromium-5-based reagent was really ideal for achieving high conversion and selectivity to this C1 benzylic ketone. We could now convert this ketone to the corresponding enone utilizing our lab's palladium-catalyzed dehydrogenation reaction conditions, and this enone was primed to undergo a Mukiyama-Michael reaction catalyzed by TBS triflate, in which this silylketene acetal could engage this enone beta position, forming this protected enolate equivalent, this enoxysilane. And we were pretty excited because we thought we could just convert this protected enolate equivalent to the corresponding natural product through a fluoride-initiated methylation reaction. And we were indeed able to complete the 10-step synthesis of xylogranatopyridine B, initiated this methylation reaction with tetramethyl ammonium fluoride, providing the corresponding highly reactive tetraalkyl ammonium enolate, and methylation provided the natural product, albeit in low yield and diastereoselectivity. However, we also got this ketone desilation product and thought that we could try a similar methylation protocol, but we were quite surprised because we actually observed really trace product and mostly recovered starting material in the corresponding methyl enol ether. So we took a bit of a step back and considered other potential strategies to input this methyl substituent, eventually deciding on undergoing a Simmons-Smith type cyclopropanation reaction of this highly electron-rich enoxysilane, and in situ desilation provided the corresponding cyclopropanol. To this structure, we could effect a cycloisomerization reaction catalyzed by this platinum catalyst, Zeiss's dimer, to effect the 11-step synthesis of xylogranatopyridine B with extremely high selectivity now. And we were pretty excited because now this was the first total synthesis of a limonoid alkaloid. With this convergent fragment coupling-based platform, we now wanted to extend this to the more complex and biologically active bis-lactone limonoid alkaloids such as granitumine A. However, something we were really aware at the beginning when we were considering planning our synthesis was the structural ambiguity in this class of bis-lactone limonoid alkaloids, especially considering the epimeric positions such as the C3, C10, and C5 position. However, we were really guided by the X-ray crystallographic studies by granitumine A, and therefore chose to target this molecule retrosynthetically first. Retrosynthetically, when we considered accessing granitumine A, we wanted to employ a similar strategy to our previous synthesis of xylogranatopyridine B. In this way, we considered installing this oxidation state at a late stage to access 3-deoxyxylogranatin F. Retrosynthetically, we once again thought we could bisect these two bonds highlighted in orange, which would bring us back to the precursors for olebaskin pyridine synthesis. When we tried to access this oxime benzoate from the corresponding exocyclic enone, we only observed rapid decomposition though. And therefore we needed to consider an alternative strategy, and therefore turned to this indirect strategy of coupling this aldehyde, ketone, and an ammonium surrogate. After aza-6-pi electrocyclization, we did in fact now access 3-deoxyxylogranatin F, and now turned our attention to this late-stage benzylic oxidation to install this methyl ether. However, after examining a variety of conditions that we previously employed in the synthesis of xylogranatopyridine B, we never observed any of the benzylic ketone or alcohol. And we were a bit surprised by this difference in propensity to undergo oxidation, especially because this chromium-5 reagent was really selective of oxidizing position A in the synthesis of xylogranatopyridine B. And so therefore we turned to this simplistic computational investigation to analyze the differences in selectivity between position A and position B. Unsurprisingly, we found in this core structure of xylogranatopyridine B that the radical and carbocation energies were more stable at position A, which eventually was the position that got oxidized. Doing the same simplistic analysis now on the structure we were trying to oxidize, this structure for granitumine A, we actually found that position B, the carbocation radical energies, were more stable. And although we didn't observe any oxidation at this position, it led us to consider that this may be a really challenging transformation to undergo, likely due to the increased steric hindrance of position A, as well as the presence of this electron withdrawing lactone. And so therefore we considered installing this key oxidation state at an earlier stage and undergoing a reduction to access granitumine A. Now, considering cleaving these two bonds highlighted in orange, this would bring us back to the retrosynthetic disconnection for Cahnava-Nagel condensation and aza-6-pi electrocyclization, bringing us back to this aldehyde and 1,3-diketone, in which the 1,3-diketone fragment could trace back to the widely available alpha-enone terpene precursor, and we thought we could access this aldehyde by employing similar logic to our previous synthesis of the C and D ring fragment. So beginning with how we approached the C and D ring fragment, which eventually became these two rings highlighted in blue in the natural product, we began with 2,6-dimethylcyclohexanone and effected a chemoselective dehydrogenation reaction employing widely available reagents, including LDA, zinc chloride, and alloacetate. And these palladium-catalyzed dehydrogenation conditions that we developed could be utilized on a 100-gram scale, avoiding any of the deleterious phenol byproduct. With this enone in hand, we could now effect a similar diastereoselective aldol reaction with 3-furaldehyde, providing this benzylic alcohol, in which this racemic benzylic alcohol could be resolved through an acylative kinetic resolution employing tetramosol. And tetramosol basically acts as a chiral DMAP reagent to resolve the corresponding benzylic alcohol to the benzylic acetate. We could now deprotonate this benzylic acetate with LHMDS to engage an intramolecular cyclization event, and dehydration with Burgess reagent provided the degraded limonoid pyroanglioside, which we could now parlay through a allylic oxidation reaction to provide a mixture of azadirylide and the requisite enal. In practice, however, we just oxidized this mixture with DMP to now access our C and D ring fragment. And so now we turn to accessing our A ring fragment, and we really wanted to begin with this widely available terpene precursor alpha-enone. But one thing we really had to consider was alpha inone was actually sold as a racemic mixture, and therefore we needed to come up with a way to resolve it to this enantiomer-enriched epoxide. Although in the literature there was a reported 5-step sequence that employed a lipase resolution, this protocol really resulted in a low overall material throughput, and we wanted to come up with a way that would enable the direct resolution of this olefin to this enantiomer-enriched epoxide. After examining a variety of conditions, we found that these Jacobson-based epoxidation conditions provided excellent diastereoselectivity and quite good enantiomeric excess to resolve this epoxide. And now we could effect a rhodium-catalyzed hydrosilation of this enone substructure to reveal this enoxysilane. And now we could undergo this really neat reaction in which ozonolysis of this electron-rich olefin and oxidative workup with Jones reagent provided this presumed tertiary carbocation in which this carboxylic acid substructure could cyclize onto this, and after subsequent oxidation provide the ketolactone. And so here we were at this challenge that I previously described in the talk where we now had to convert a ketone to a 1,3-diketone. And we examined a variety of different conditions to do this and eventually found that undergoing an initial palladium-catalyzed dehydrogenation utilizing these conditions developed in the Stahl group provided really excellent chemoselectivity to provide this enone here, in which undergoing a nucleophilic epoxidation provided an inconsequential mixture of alpha-beta keto epoxide diastereomers, and isomerization of this keto epoxide to the corresponding 1,3-diketone, now employing these newly developed palladium-catalyzed conditions, utilizing palladium acetate and this bi-aryl ligand X-phos. With a really robust approach to our two key fragments, we were ready to test the key Knoevenagel condensation, where at least initially we were expecting to get this diketone intermediate, where we would have to differentiate between ketone A and ketone B. Ketone B in this molecule would eventually become this benzylic alcohol in the natural product. However, this was one of those extremely fortuitous days in lab where we got this really unexpected product, this 2H-pyran, where ketone A underwent this amazingly selective oxo-6-pi reaction. Now this was extremely fortuitous to us because this enabled a selective protection of ketone A, allowing us to manipulate ketone B to the requisite benzylic alcohol. Utilizing a modified Lusch reduction employing trifluoroethanol instead of the more nucleophilic methanol to prevent addition into the 4 position of this pyran. We now had to figure out a way of converting a pyran to a pyridine, and upon heating the reaction mixture up with hydroxylamine, presumably initially underwent a retro-oxo-6-pi reaction, followed by condensation with hydroxylamine and azo-6-pi reaction, provided this intermediate structure, in which we could diverge in reactivity. In one sense, we could lose water from this pseudo-benzylic position, this red hydroxyl group, to reveal the corresponding pyridine and oxide, which we confirmed by reduction to 3-deoxyxylogranatin F. But gratifyingly, we could also lose water from this blue hydroxyl group to reveal xylogranatin F, at least the proposed structure, where unsurprisingly, when we confirmed our spectroscopic data to the reported data, it didn't match, and we were somewhat expecting this based on the structural ambiguity, and took this one step further to granitumine A through chlorination of this benzylic alcohol in displacement with sodium methoxide. And so at this point, we really wanted to resolve the structural ambiguity with xylogranatin F and the related congeners of the bis-lactone limonoid alkaloids. To be confident that we synthesized the proposed structure, we got a crystal structure of our synthesized intermediate, and it did in fact match the proposed structure of xylogranatin F. We took this forward through a similar sequence, chlorination of this benzylic alcohol with thionyl chloride, and displacement with zinc acetate, provided now the revised structure of xylogranatin G, which upon simple hydrolysis revealed now the revised structure of xylogranatin F. So today I've told you about different strategies we've employed for de novo pyridine syntheses to access molecules such as xylogranatopyridine B, developing this modified Libeskind pyridine synthesis, but also accessing bis-lactone limonoid alkaloids typified granitumine A, utilizing an unconventional pyran to pyridine conversion. We also developed a variety of new methods and protocols, including palladium-catalyzed beta functionalization reactions, structurally reassigned a variety of bis-lactone limonoid alkaloids, and we're currently investigating the PTP1B inhibitor activity with Professor Loria's group at Yale University. So with that, I'll first conclude by acknowledging my advisor, Professor Newhouse, who gave me the tremendous opportunity to work on this really exciting class of molecules. And this has really provided an excellent opportunity for me to get to work with some really tremendous chemists who were acknowledged on the slides, including both talented graduate and undergraduate students. And I have to thank my collaborators, including Professor Pat Loria and his group, who are now investigating the biological activity of these molecules, and the sources of funding, including the BMS and NSF graduate fellowships. And once again, thank you so much for watching my talk, and thank you, Matt, for giving me the invitation to be part of this really exciting series.
Thank you for tuning in for this Research Spotlight episode, and thank you to Alex for a great talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.